Okay, so to finish up the proof of proposition 5.32, we're going to remember that what we wish to show is that for S and T, which are right invertible operators with equivalent kernel dimensions, there exists a path from S to T, with every value of the path being a right invertible element of f of n. Now, we're going to borrow to prove this, we're going to borrow a technique that we used a couple sections back, where we have this sequence, this path of u sub lambdas, where u is a unitary operator, and we're going to have u0 equal I and u1 equal u. And specifically, we're going to pick this u such that the kernel of SU is equal to the kernel of T. Now, obviously, this is going to give us that S and SU are connected, so and in Fn. So, without loss of generality, we can assume, we can take as our original assumption that the kernel of S and the kernel of T are in fact equivalent. And this follows from the choice of u that we've made. Now, by proposition 4.37, there exists a partial isometry W with range W with the range of W being equal to the orthogonal complement of the kernel of S, and which is then equal to the orthogonal complement of the kernel of T. And again, this is just going to follow from the fact that the kernel is always a closed subset or subspace. So why do we want to invoke this isometry W? And it's going to be because it gives us that SW and TW are in fact invertible. And because of the proposition that we proved last time, corollary 530, what we get is that they must then be path connected, where every element of the path is in fact an invertible operator. So what we're going to do is we're going to name this path J sub lambda, and we're going to use the fact that that W is a partial isometry and that J lambda is a path of invertible operators to continue the proof and show that they are in fact path connected with a right invertible valued path on Fn.